Dieter Fox, his senior robotics research director at NVIDIA and professor at University of Washington in Seattle, and a great contributor to SLAM, as you know. So, Dieter?
Yeah, thanks a lot for giving me this opportunity. The title is from a talk that I gave recently, which was an hour long. So I thought, but rather than trying to squeeze an hour-long talk into these 8 to 10 minutes, I decided I'll just mostly actually talk about some lessons I learned in 30 years in robotics, which seems easier to summarize in 10 minutes. We are currently seeing, I think, really dramatic developments in capabilities of large language models, vision models. So everybody, of course, heard about ChatGPT. And we're also seeing now already that these developments and these techniques are making their way into robotics. And I think we're already seeing some quite strong impact on the capabilities now also on the robotics side. And of course, the question that we as roboticists are constantly getting asked is, or I'm getting it asked a lot, is like, where is now your RobotGPT, right? Because the reasoning is that, okay, the language people, they figured out ChatGPT, and we're seeing all these developments in computer vision, and these roboticists are just so slow, right? And we are constantly behind. So the question is, how close are we to this RobotGPT moment? And many of you heard of Daniel Kahneman, especially in the context of System 1 and 2, thinking fast and slow. And he already also realized through several studies that people are really bad at making predictions about the future, and especially when it comes about planning, how much something will cost, how long something will take. So what he suggests is that if you want to make any planning or prediction about certain projects, then you should take similar things, similar other use cases and projects into account in order to make your predictions. So let's just do that and look back at some of the developments that I've seen over the last 30 years. So I started in robotics in 1994. We participated in the AAAI robot competition in Seattle with Sebastian, Wolfram, and others. And at the time, the key sensor modality that we used were sonar sensors, and all the competition tasks were about mapping and navigation. And we did a reasonable job, but robots often still got lost. The maps were not very high quality. The robot might also crash into things. So it was actually very hard to make these robots work with the sonar sensors. I'm sure many of you haven't even started working with them because you're already doing computer vision and LiDAR. Then going 3 years forward, we got our hands onto these 2D LiDAR sensors, laser scanners by SICK, and that, of course, made a huge progress in robot navigation and mapping capabilities. They had, I think, a tremendous impact, and Roland already mentioned that yesterday as well. And for example, these museum tour guide projects that we did would just not have been possible without LiDAR scanners at the time. But I think it's fair to say that 27 years later, we still haven't really figured out how to really robustly out-of-the-box navigation systems for indoor navigation. And I think one of the key things is, of course, changing environments and semantic reasoning. The next development was also, of course, more on the algorithmic side, probabilistic robotics, Bayesian estimation, and decision-making. And I think what these techniques led to is not like an incredible jump in capability suddenly like LiDARs, but I think they led to some steady progress in developing robust navigation system, right? Especially on the localization, SLAM, and also planning side. At the time, we also thought, of course, if you do a good enough job in modeling your sensors, modeling your dynamics of your system, that more or less you can solve robotics. But I think we kind of didn't put enough emphasis on questions like semantic understanding, visual understanding. So these kind of techniques are extremely well suited for things like sonar and LiDAR, but not so I think, crucial, let's say, for computer vision techniques. And famously, Hugh Durant-White already 20 years ago stood up and said, SLAM is solved, and I think we all agree it's still not quite solved, right? Like representing environments and things like that. Then 2007, of course, DARPA Urban Challenge, autonomous driving. And here's the winning team from CMU, the BOSS team. And the key sensing capabilities were actually 3D LiDAR scanners by Velodyne. What that urban challenge led to is then, for example, Sebastian convinced the team at Google to start autonomous driving, which is now the Waymo. That led to huge investments by all the car manufacturers to get involved in this area. And I think they've made, of course, tremendous progress in that. But at the time, when we discussed these topics, again, this is 17 years ago, people would have said, like, my kids, they don't need a driver's license anymore, right? Because it's going to be solved by then. And these kids by now are all old enough that they already have a driver's license. So these predictions were also quite off in the estimates of how long it's going to take to make this work. And then 2010, depth cameras came around, and that was a huge moment, I think, for the capabilities in robot visual understanding, especially also manipulation. And it kind of opened up the whole world of computer vision to the broader robotics community because it combined vision with, of course, 3D shape information. We made really good progress on things like modeling objects in the world, modeling environments, 3D modeling of environments. And this also when I then started working a bit more in manipulation. And at the time, of course, I thought that by now, object manipulation in environments would be totally solved, right? And I think we all agree that we're still not quite there yet. It's kind of always surprising because many of these fundamental problems about how do you even model and represent an environment and semantic understanding of environments are just extremely hard, and we just didn't foresee all these complexities that would come up. Moving forward, 2 years later then, of course, deep learning really had its big moment. On the one hand side with AlexNet on the ImageNet competition, but then also, of course, with DeepMind, with AlphaGo and deep reinforcement learning on raw visual data. So all of these had, I think, also very foundational impact on robotics because suddenly you could automatically learn low-level features from visual data. Reinforcement learning would become like possibly viable for robotics because they showed again on Atari games at the time mostly that you can perform reinforcement learning from raw visual data. But again, we also realized that it's much harder than we thought. And nowadays, if you see what's going on in a lot of the developments, is people do behavior cloning rather than reinforcement learning because it's still so hard to get reinforcement learning to work in the real world. And now, very recently, we had the big ChatGPT moment, and I summarize generative AI, which is these kind of techniques on the computer vision side, for example, CLIP, where people showed that you can train very, very robust visual embeddings and representations just from raw internet image data connected with captions, for example. And I think ChatGPT was really an aha moment where people felt like, oh my gosh, this is a dramatic step upwards in the capabilities of these reasoning systems. And then it's not only about, of course, language understanding, but also if you look at things like image generation, image understanding, semantic understanding of images, and most recently, of course, now the developments in video understanding and video generation, which relates to what people call these world models, are, of course, I think also very important developments we are seeing there. So where are we now with RobotGPT? So if we go back and take these lessons from the past, of course, then it's clear that we totally overestimate how quickly we're going to make this progress right now, right? And we just underestimate how hard it is to build really capable robot systems, especially capable robot systems in the open world, right? And that is kind of one of the key things that these new models might add to what we have right now. So on the one hand side, you would say, oh, well, it's going to be another 50 years at least or so until we have anything that is a robot with open world capabilities. But at the same time, I'm willing to more or less just throw all this experience and all the things I learned overboard and just say that I feel like while the RobotGPT moment is not quite around the corner, it's not going to happen in the next 2 or 3 years, but at the same time, I think we're going to see drastic progress in robotics due to these new generative AI capabilities. So I am absolutely aware that I'm very likely to totally overestimate those capabilities and underestimate how long it's going to take, but I'm willing to make that bet. And I think why we're going to see these improvements is really that on the one hand side, there's a lot of new capabilities with respect to open world reasoning, also the sensing modalities that are just so crucial for robotics, like language, image understanding, and also video understanding, temporal image understanding are becoming better and better. And we see the development of these very large, for example, transformer diffusion models with tokens kind of being a unifier across many different modalities. And I think also, of course, what we're seeing is a lot of money going into these areas, also in robotics now, humanoid robots. And I think that's going to help us on building better hardware and also generating a lot of data that we need for these models. So if I have 10 more seconds, then just briefly, I think we as a robotics community should not just watch these things happen and just try to leverage them in robotics, but we should actively participate in developing these models and become key players, because we are the ones who know what it takes to make real robots work. And I think I gave in another talk, of course, I think, for example, simulation is going to play an important role in generating data for training these robots. And if you want to know more about this, I gave a keynote at RSS recently. For example, there's on YouTube, you can find a video where I'm giving more ideas or more of my thoughts on how we can get there. Thank you very much.
Thank you, Dieter. Questions?
Mine? Yeah, okay. I'm over here. Nope, to your left.
Well, to my left?
Yep, there.
Left.
Hey, Dieter.
Okay.
Great talk, thank you. I hear a lot of people talking about the ChatGPT moment for robots or RobotGPT or what have you. And I'm curious, even if we manage to get similar capabilities onto an edge device with the multimodal functionality that makes it applicable to robotics, would that actually be useful for people? Because ChatGPT is not exactly, even with the recent updates, is not exactly something I'd want to control a physical object. So even if we do have that ChatGPT moment for robotics, is it enough to put them out into the real world? Is it sufficient?
Yeah, I think one crucial piece is that these models, and that's in line, of course, with ChatGPT, is that we can't expect them to be 100%, to work 100%, right? So if we want to transfer that to robotics and make them really useful, we need to make them robust to failures, right? Which means we cannot expect them to operate 100% all the time, but they need to be able to, if they fail, to retry different ways of achieving a task, or maybe interact with people and get help from people. And I think all these technologies can really help with this more kind of what we call open world reasoning and the language interfaces, for example, for talking to humans. Application areas, I would say, of course, in the home, helping people with disabilities, elderly people, robots in hospitals. I think we're going to see very viable use cases, at least for these robots. In industrial settings, for example, I think there is where precision really matters, and that is more where I think we can learn a lot from the general technical insights, but it's not going to be just like, a RobotGPT in a factory where you just tell it, okay, this is what you should assemble, and it's going to be able to do that.
Thank you. I've seen another question there.
Yes, thank you for your talk. In developing something like RobotGPT or something similar, what kind of challenges do you expect in safety and security of developing something like that?
Yeah, that's a great question. I think at this point, there's two levels of safety and security, right? Of course, there's the pure, let's say, physical safety, which we as roboticists really have to to worry about, for example, with manipulators, that they don't just hurt the person around them. But then when we go to these more open world systems, of course, there's then the safety that is also one level up, right? Like, so what happens if the higher level system tells the robot to do something that seems physically safe at the moment, like pressing a button or something like that, but what that button press actually achieves in the real world can be something that is clearly not safe or things like that. I think there's a lot of work that just has to be done in that area, right? And that also comes along with these developments in making these large language models in general more safe. So it's clearly a wide open area that we need to look into.
Thank you.